All right, let's get right into it. Today we are breaking down two incredibly powerful string algorithms that you absolutely need to know for coding interviews and competitive programming. We're going to cover how they work, what makes them so fast, and most importantly, which one to choose when you're under pressure.
So here's our game plan for today. First, we'll set the stage with the core problem we're trying to solve. Then we'll bring in our two main players, hashing, which is like a super fast fingerprinting method, and the Z algorithm, a totally different but incredibly precise approach. After that, we'll dive into the biggest weakness of hashing, the collision problem, and finally we'll put them head to head with some exam strategies so you know exactly what to do. Have you ever really thought about that? You hit Control F to find a word in a huge file and boom, it's just there. It feels instantaneous, almost like magic. Well, it's not magic. It's the power of really efficient string algorithms, the kind that blow the slow, obvious methods out of the water. At its heart, the task we're tackling is pattern matching. Now, the simple, brute force way to do this is to just check every single possible starting spot. But if your text has n characters and the pattern has m, that approach takes O of n times m time. That means the work grows proportionally to n times m, which can get out of control really, really fast. For big files, it's just not good enough. We need to be smarter. We need solutions that work in linear time. Okay, first things first, let's get our terminology straight, because the details really matter here. A substring is just an unbroken, continuous piece of a larger string. Think of it like taking a slice right out of the middle of a word. Now, a prefix is a special kind of substring. The rule is simple. It has to start at the very beginning, at index 0, no exceptions. And you guessed it, a suffix is the exact opposite. It's a substring that has to include the very last character of the original string. Substring, prefix, suffix. Getting these three down is absolutely foundational for everything we're about to do. Okay, on to our first big technique, string hashing. And the idea behind this is just brilliant. Think of it like this. We give every single string a unique numerical fingerprint. So now, instead of comparing two potentially very long strings character by character, we just compare their two numbers. And comparing two numbers? Well, that's incredibly fast. It's constant time, or what we call O of 1. So you might be wondering, how do we actually calculate that fingerprint? Well, it all comes down to this. The polynomial hashing formula. It looks a little intimidating, but think of it as just a weighted sum. We take each character's numerical value, say its ASCII code, and multiply it by a power of some base A. That mod B at the end? That's just a clever trick to make sure the final number doesn't get ridiculously huge. Let's make this real with an example. Take the string Ali. First, we convert each letter to its ASCII code. Then, we pick some constants. Let's say A is 3 and B is 97. We just plug all those numbers into our formula, do the math, and out pops a single number, 52. And that's it. That's the unique fingerprint for the string Ali. Now this right here, this is what turns hashing into a real superpower. See, calculating the hash of every possible substring one by one would be way too slow. So instead, we do a really clever pre-processing step. We calculate the hashes of all the prefixes just once, and we also pre-calculate all the powers of A we'll need. Once we have those, we can use this formula to find the hash of any substring, no matter how long, in a single calculation. That's constant time. This is the trick that makes hashing an absolute game changer. Okay, it sounds perfect, right? But there's a catch, and it's a big one. What if two completely different strings just happen to produce the exact same fingerprint? Well, that's called a collision. It's the main risk you take with hashing, because your algorithm will think the strings are the same, even when they're not. The probability of a collision is actually way higher than your intuition might tell you. It's a lot like the famous birthday paradox. If you have a room with just 23 people, there's already a 50-50 chance that two of them share a birthday. It's the same idea with hashing. As you generate more and more fingerprints, the odds of two of them matching by pure chance go up surprisingly fast. And this table just drives the point home perfectly. Take a look. If we're just comparing two strings, a modulus of about 1 billion is totally fine. But look at that last column. What if we're comparing all pairs of strings among 1 million of them? With that same modulus, a collision is a practical certainty, a 100% chance. You have to crank your modulus B up to a massive number, like 10 to the power of 18, to get that probability down to almost 0. So how do we protect ourselves? Here's your exam playbook. First, always choose large, random prime numbers for your constants A and B. For extra security, you can even use two totally different hash functions. The odds of a collision on both of them are tiny.
And here's the critical takeaway. Whatever you do, never use a power of 2 for your modulus b. It might seem convenient, but it's a well-known vulnerability that can be exploited to cause lots of collisions on purpose. Okay, so that's hashing. Now let's pivot to a completely different way of thinking with our second tool, the Z algorithm. If hashing is all about speed and probability, the Z algorithm is all about precision and certainty. There's no chance involved here. It's a deterministic method that is guaranteed to give you the right answer every single time, and it also runs in linear time. The entire heart of this algorithm is something called the Z array, and what it stores is actually pretty simple. For every index k in our string, the value zk tells us one thing. How long is the substring starting right here at k that also happens to be a perfect match for the beginning, the prefix of the whole string? It's like a prefix matching ruler we slide along the string. Let's watch it get built. We just move from left to right. By the time we get to index 6, the algorithm looks at the substring starting there, which is ACBA. It compares that to the prefix of the whole string, and what do you know? It's a perfect match for 5 characters. So we write it down, Z of 6 equals 5. Now you might be thinking, wait, just comparing characters at every spot sounds slow, and you'd be right. But here is the absolute genius of the Z algorithm. As it scans, it keeps track of a range, or a Z-box, that it already knows is an exact copy of a prefix. So when it gets to an index k that's inside this box, it can use an already computed Z value from earlier in the array to get a huge head start, often skipping tons of comparisons. It's all about reusing work you've already done. And here's that trick in action. After we found that Z6 was 5, we now have a Z-box that covers indices 6 through 10. So when we move to index 7, we see it's inside our box. We can use the value of Z1, which is 0, to instantly know that Z7 is also 0, without a single character comparison. This constant reuse of information is what makes the whole algorithm fly by in linear time. Okay, that's cool, but how does this actually help us find a pattern? Well, this is the classic exam trick. You take your pattern, P, and your text, S, and you mash them together into a new string, P hash S, with a special character in between that's not in either. Then you just compute the Z array for this new combined string. Anytime you find a Z value that's exactly equal to the length of your pattern P, you've found a match. All right, let's bring it all together. You're in an exam, the clock is ticking, a string problem pops up. Which of these tools do you reach for, hashing or the Z algorithm? It's not always an easy choice, so let's put them side by side. Here's the fundamental trade-off. Hashing is like your fast, flexible, all-purpose tool. It's usually easier and quicker to code, but you're always playing the odds, hoping you don't get a collision. The Z algorithm, on the other hand, is your heavy-duty precision instrument. It's a bit more complex to implement, especially under pressure, but it is guaranteed to be correct 100% of the time. Okay, quick revision time. Here's what you absolutely have to lock in. For hashing, master that O1 formula and know exactly how to pick good parameters to avoid collisions. For the Z algorithm, you need to know the definition of the Z array cold, and don't forget the P-sharps trick. But honestly, the best advice is to code both of these from scratch, over and over until it's pure muscle memory. That's how you walk into an exam with confidence. So there you have it, 2 incredibly powerful but very different tools for your arsenal. You know, being a great problem solver isn't just about knowing how the tools work. It's about having the wisdom to know which one to pick for the job at hand. So the next time you're faced with a string problem, what's it going to be?